Good morning, everybody, and welcome. Thanks for joining in to virtual seminars. So the work I'm presenting here today is part of a project funded by the Bushfire Natural Research CRC. So this is a small project with a total of 1 FTE that's been ongoing for the last about 6 years now, and it consists of 3 of us here in the bureau, myself, Imtiaz Darcy, and Paul Fox Hughes. So this is one of the last pieces of research that we have undertaken as part of this project. So our project is going to end this June. Anyway, I think this is an interesting piece of work. So there's a lot to be done in this area, and we are, like I mentioned in my title, is just a preliminary examinations, and yeah. So okay. So just to give you some backgrounds, I'm on to slide 2 now. Hopefully people can see it. So just to give you a bit of background, we got this project, it's called improvements to land drainage measures and forecast, in short. So the motivation of this project came from the fact that the managers in fire agencies and also people from extreme weather desk identified limitations with the current operational soil moisture deficit models used in McCarthy's Forest Fire Danger Index, and they wanted something a bit more accurate and realistic. So so soil moisture deficit is used in FFDI calculations to estimate fuel availability. So that term, which is a proxy for fuel availability in FFDI, is called the drought factors. And currently we are using very simplified water balance model designed in the 60s to do handheld calculations. So there were research done which recommended that employing a multi-layer soil model is desirable to estimate the soil moisture dryness, because the relationship between fire and soil horizon actually changes with season. So great progress on soil moisture estimation has been made in recent decades, especially in the form of land surface modeling and microwave remote sensing. Also, pertaining to these talks, so also there's been a lot of progress made in estimating the live field moisture content, especially using optical remote sensing data at a continental scale. So like I mentioned before, our project, one of the main aims of our project is to estimate soil moisture at a high resolution over the whole Australia. And Imtiaz designed an offline land surface modeling system which can analyze soil moisture at 5 kilometer resolution on a daily time steps. So this system we call Jasmine. So it's short form for the Joules-based Australian soil moisture information. And Joules is the land surface model we used here in the Bureau for our weather prediction and seasonal prediction. And there's a capability to run Joules offline and driven by observation-based inputs, and among many variables that Joules estimates soil moisture is one of them. So Jasmine provides soil moisture at 4 layers. So the total soil moisture, total soil profile depth is 3 meters. So from the first layer is about 10 centimeter deep, 0 to 10 centimeter. The second layer is 10 to 35 centimeter deep, and third layer is 35 to 100 centimeter deep, and the fourth layer is 100 to 300 centimeter deep. So it's total 3 meter deep soil profile. So we published a Bureau research report on the development and evaluation of this Jasmine system, which is publicly available. So if people are interested, you are encouraged to go and browse for those Bureau research reports, or contact us and we can provide you a soft copy of the report. Okay. I'm having trouble moving to next page. It's funny. Okay, so while we are here, I just want to advertise that Jasmine data sets are available through our thread server. So like I mentioned, this is a research product, but we have provided that through our threads for those people who are interested, and there are a few people in our end user community who use these data sets to analyze or to use for their research work. So the data is available in netcdf formats as annual cubes, and we also developed some calibrated products. So the idea is to calibrate Jasmine so that it can be ready-made use in the current operational systems, replacing the existing operational drought indices. Okay, so moving forward. This is quite slow. Darren, can you see my slides okay?
Hello, Vinod. Yes, we are seeing your slides, but they are a bit slow to
yeah,
progress.
I'm having trouble moving to my next slides, but anyway.
Yeah, this is Dave. I noticed the other day in a meeting with a large number of people, it has some feature where it sort of tries to make sure everybody can see it before you move to the next slide. So it's very slow, but it's because everybody needs to sort of get to the next slide before it goes, I think. That's what I observed from a meeting with 200 people in it.
All right, thanks.
Anyway, we'll wait patiently, and then when you're ready, you can talk. Thank you.
Okay, so moving on to the next slide. So there are two parallel projects funded by the CRC. One is our project to determine soil moisture at high resolution, and also there's a group working at ANU. This is led by Marta Yebra at the ANU to develop live fuel moisture content data. This based on the MODIS reflectance data, where they retrieve live fuel moisture content values by inverting a radiative transfer model. So this is also a physics-based system. So this data set is this forms part of the Australian flammability monitoring system. So there's a nice website that Marta and her group has developed, and you can go and browse the data set data time series. So the data set is available at 500 meter resolution every 4 days. So Marta has done some evaluation, which is described in the paper, which I have mentioned at the bottom of this page. So she evaluated this data set against in situ observations of about 32 locations for about 360 observations, and she found that the product has rather good skill with an R score of 0.58 and mean score error of about 40%. So I would encourage you to go and look at that paper published by Marta in Remote Sensing Environment if you want to learn more about the project. So he is quite keen to compare these two products and, if possible, identify some relationships. So that's the motivation of this work. So there's a scale mismatch between these two products, as you might have noticed. So Jasmine is available at 5 kilometer resolutions, which is much coarser than the live fuel moisture content data. So so what we have done is we upscaled the live fuel moisture content data from 500 meter to 5 kilometer resolution by taking average of all the grid points that fall within each Jasmine pixel. So I'm waiting for the next page to show up.
While you're waiting, Vinod, we've had an online question saying,
Sure.
could you define live fuel moisture content? So if you could give a little description while we're waiting for the next slide. Thank you.
Yeah, sure. Yeah. So live fuel moisture content is might have. So it's the amount of water. So the way they calculate is traditionally they weigh it before and after drying, and it's basically a ratio of your weight before and after drying. So it can go up above 100%. I'm not a great deal of expert in live fuel moisture content, so maybe if you want to learn more, ask Marta about it. So that's my limited understanding about it.
Thank you.
Okay, let me try again. No. Right. Okay. So while we are waiting, so the idea is to come up with very simple models to describe the live fuel moisture content based on soil moisture. So we haven't considered a lot of other variables. So we are just focusing on the relationship between soil moisture and live fuel moisture content here. And also the Jasmine is hosted by the Australian Flammability monitoring system as well. So, but it's only available at the top two, only top two layers soil moisture content is available through the Australian Flammability monitoring system. So if you want to have all the 4 soil layer, then you might have to access it through the thread server. And like I said, if you are interested in that data set, contact us, and we are happy to help you downloading it. This is taking a long time.
So Vinod, I'm noticing that you're getting a poor connectivity message coming up sometimes saying that you have bad Wi-Fi or low Wi-Fi or something. I'm just wondering whether you want to email me your presentation, and maybe if I display it, it may be a bit more responsive.
Okay.
Up to you. Just, yeah, it's not moved on yet from the Australian Flammability monitoring system.
I mean, it worked pretty well last time with Peter's presentation. So disappointing. I can't even explain. escape from Wi-Fi. Stop sharing my.
Maybe it's your computer that has been slow rather than the system.
Not
But
sure.
anyway, that's okay. We'll wait patiently. If anyone else has a question, you can get in and ask it. And try not to distract Vinod too much from whatever else he's trying to do.
Okay, so
in situ locations.
Yep.
Good.
Okay, so good. So I can now move to my next slide. Anyways, sorry for all the trouble, but so our strategy or our starting strategy is to analyze the relationship at about at various locations, which corresponds to 3 soil moisture networks. So Cosmos, OSFlex, and OSNet are 3 well-known soil moisture networks in Australia, and in total it comprises of about 60 sites. The reason we selected these sites is we know that Jasmine has got pretty good skill over this site, so we did a fair bit of verification and evaluation of Jasmine over these sites. So the table that I'm showing here is actually lifted from one of the a manuscript or a paper we published last year in Agriculture and Forest Meteorology. So which basically shows that Jasmine has a good skill over this site. So the scores I'm showing here are the correlation, the anomaly correlation, the bias and unbiased differences. So I'm actually verifying an absolute soil moisture content here. So in short, so I just want to highlight that you know, the average skill over all these sites is pretty good adjustment. Okay. All right. So just looking at one of the side. So this is Baldry, which is reforested and pasture land in New South Wales. So what I'm plotting here is the 4 soil moisture from the 4 Jasmine layers, and also the live fuel moisture content, and also the bars represent the 24-hour accumulated rainfall from the AWAP dataset, which is also at 5-kilometer resolution. So the blue line represents the top 10 centimeters soil moisture. The green line represents the second soil layer, which is the 10 to 35 centimeter. The red line represents 35 to 100 centimeter, and the pink line represents the bottom layer, which is 100 to 300 centimeter. So what you can see is the top 2 soil layers show very large temporal variations, which is understandable because these 2 layers are more subjected to the weather patterns, whereas the bottom layers has a much smooth temporal variations. Especially the third layer does show some seasonality, but because the top 2 layers act as a natural filter, the moisture is percolated much slowly onto the third layer, and the bottom layer has a much less sizable temporal variability because possibly pertaining to its depth and also the thickness of the layer. So and the live fuel moisture content, one thing you notice, it is got pretty strong seasonality in it, and also it has a much large it's much stronger temporal variation than, say, the third layer, but much smoother than the top 2 soil moisture layers. So Okay, so what I want to, so we did a correlation analysis of live field moisture content with these different layers and a combination of soil profiles, and what we found was that if you combine the first two layers, that gives you a soil profile of 35 centimeter depth from 0 to 35 centimeter gives you the highest correlation. So this is shown in the next slide. Ignore the green box on this for the time being. So the light pink actually shows the correlation, the lag correlations of the 0 to 35 centimeter layer against the live field moisture content. So you can see that. So this is for different land class, based on the observation land use classification, or the in situ land use classification. So you could see that for grasslands and woodlands got fairly strong correlation. But the lag actually varies from site to site and also from land use types. So the other thing we found that obviously both the live field moisture content and soil moisture content data will have a lot of noise in it, short spikes, which could be due to say short precipitation events and other data uncertainty. So we could actually apply a temporal filter to the soil moisture data, and we observe that the lag correlation actually improves a bit. But it's sort of applying a temporal filter to soil moisture basically means that it's because it's a gravity-driven layered model. It corresponds to expanding that soil profile somewhat, and such temporal filters have been successfully applied in soil moisture in various studies, especially estimating roots on soil moisture from remotely sent. So from that measured by the remotely sensed satellites. So if you apply temporal filter, you can actually improve the correlations. But I'm also wary that applying a temporal filter and looking into lag correlation can be a bit tricky, because you might get some artificial correlations due to that smoothing. So this is something I have to look a bit more careful and in detail. Okay, so moving on to the next slide. So stepping up further back, we know that we already have some measures which is quite similar to the live field moisture content. For what I mean is the drought factor in the McCarthy's FFDR is actually a measure of the fuel availability. So basically, how much fuel is available to burn for a particular day, and it's defined as a function of soil moisture deficit and rainfall for the past 20 days. So the soil moisture deficit is actually a measure of the, and rainfall is considered as a measure of short-term drying in drought factor. So if I do similar correlation analysis, so this is just correlation, not lag correlation. So, and against the live field moisture content data, you could see that for some. So yeah, I just want to mention that this soil moisture deficit I'm using here is derived using a calibration method we applied in other studies. So this is basically a minimum maximum approach where you rescale your soil moisture using by finding the minimum and maximum of the time series, and then rescale it to the soil moisture deficit scale required by the drought factor, which is from 0 to 200. So 0 means very saturated soil, and 200 means very dry soil. And again, so the color bars show different soil profiles that you could derive from Jasmine. so in short, the takeaway point is the 0 to 35 centimeter layer has the highest skill in provides the highest skill in this relationship. I also looked into just the Drought 10, that is the soil moisture deficit 10 in the drought factor. You could say it's a similar skill to drought factor here, but drought factor at sometimes have higher skill possibly because it also consider precipitation, which is a fact, which can be a factor influencing the life fuel moisture content data. So this analysis that we did using this again soil moisture deficit derived out of Jasmine and the live fuel moisture content from the AFMS, so just a frequency distribution of all the points which corresponds to hotspot detected from the MODIS FRP data. So you could see that for grass, so the left two panels actually corresponds to the grasslands. So you can see that the fires over grasslands over very dry soil normally, and also for live fuel moisture content, it's usually less than 50. So when the fuel is very dry. On the right, it has the same plot, but for the evergreen forest, and this is very interesting and also highlights the complexity of both soil moisture and live fuel moisture variability, because it actually shows that for evergreen forest, fire actually occurs at much wider range of soil moisture, and also the fuel is much better in evergreen forest when the fire occurs. So I could look into the scatter plots of the live fuel moisture and against drought factor and identify what kind of relationship I can derive from there. So I applied a log transformation to the live fuel moisture content data before deriving any regression relationship, just to compress this positive, because LFMC is a positive, definite, and open-ended data set. We, however, present the results only after transformation back to the original unit. So this is just some skill scores we estimated from after using drought factor as the predictor for a live fuel moisture content. So on the left is the correlation. So you could see that this skill actually varies from location to locations. There are places where it shows very good correlations with the original live fuel moisture content data sets. Generally, there is no bias in the prediction, but we observe very large mean score differences of the order of about 50% of the dynamic range. So quite large root mean score differences has been observed from the prediction of this model. So moving back to the soil moisture, again, we can do similar stuff. So, at each and every site, we could actually loop through. So, basically as a data analysis exercise, you could loop through different degrees and different lags and identify the polynomial and the lag, which gives you the maximum correlation between the live fuel moisture content and that predictor. Observe live fuel moisture content and that predictor from the soil moisture from the model, polynomial regression model. So we found that we can construct a model with a polynomial degree of 9 and a lag of 1 day, which give us fairly reasonable skill. So this is just to keep simple the model simple. We can. The lag obviously varies from site to site, but we found that most of the times the best skill is obtained for a lag of 1 day. So if you apply that model for the whole country and assess the correlation bias and root mean square difference. You could see there are a lot of sites which gives you strong correlations. There are sites obviously which have less. In over Tasmania, the model give you good skill. The root mean score differences have decreased compared to the model based on the drought factor, which is good, but still there are the arrays are of the order of about 30% at some locations. Okay, so this again another evaluation we did. So it's basically collocating the predicted and the observed live field moisture or the measured live field moisture content data over grid points where the MODIS fire radiative power data set where there are hotspots detected by the MODIS instrument, and also we can use the MODIS land use land classification data to classify each and every site, and then segregate based on the land use land classification. So basically, this is a scatter plot against the fire radiative power, which is on the x-axis, and the fuel moisture content estimated, the original fuel moisture content and the predicted live fuel moisture content. So the color bar actually the colors actually signify the density. So there are more number of data sets where the red color is, and the less number of data points where there are blue colors. So you could see that say for example over grasslands, the predict live fuel moisture content can over predicts the live fuel moisture content, also over crop plants. It gives you a good prediction over the evergreen broadleaf forest and also the woody savannas, even though there are a few over prediction of these sites as well. Check again. Oh, sorry, I'm stuck again. While we are waiting, do people have any questions? I'm happy to take any questions.
Just unmute yourself if you would like to ask a question.
Vinod, Michael here.
Yeah.
So again, with the live fuel moisture content and what it is, so what's the relationship between that and the curing as used in the grassland fire danger index?
That's a difficult question for me to answer. I understand it's a bit different, but I haven't looked at the curing data, so I'm not really sure what it is. Sorry, yeah, not much help there.
Okay, no worries.
Okay, yep. Looks like we have. Okay, so one of the things we noticed is the annual cycle of both the live field moisture content data and soil moisture content data are quite different. For example, the plot shown here is again our Baldry, which is in New South Wales. So you could see that the soil moisture peaks much earlier than the live fuel moisture content data. So there are studies which shown that the seasonal variations in live fuel moisture content data is the seasonal variations in live field moisture content data is affected by a lot of other factors, especially the plant physiological factors. So if we want to model live field moisture content data accurately, we have to consider a lot of these physical the other physical factors. Unfortunately, we can't do it here, but we can easily apply simple models to simple mathematical models to capture this annual cycle. So what we did here is, so the idea is to develop a model which is a combination of a model that predicts your annual cycle and also the residuals of the live field moisture content data is predicted by the residuals of your soil moisture content. So basically what we are trying to do here is come up with an annual model based on a time function. So so we are doing here using Fourier series to fit the annual cycle of both live field moisture content data and the soil moisture content data, and then remove that annual cycle from the original time series and use and fit the residuals between the two live time series using a simple linear regression model to come up to see whether that residuals or the short-term variations in soil moisture content can predict the live field moisture content. So this is one of the this is an example for the evaluation of the fit to the mean daily value. So this is over one of the sites in Osnet in the Murrumbidgee catchment. So you could see that the annual so if the site deviates little from the annual cycle, then annual model would be a good approximation for the live field moisture content time series. And you could see that at sites, it actually provides a good estimate of the live field moisture content dynamics and also the soil moisture content. And then once you remove and compare the residuals between soil moisture content and the live field moisture content, the soil moisture, we can apply a linear regression model of soil moisture content to predict the live field moisture content. So what we are trying to do is a linear combination of that annual model plus the model of the residuals to predict the live field moisture content to each location. But we have also seen that it doesn't work always. For example, over Tumbarumba in New South Wales, again, you know, we don't see that strong relationship between the residuals, and we often get a poor R square. So again, I just want to highlight that there are issues in the model that we might have to address in future. So if I apply the model to the whole of Australia and again do similar skill assessment, then I get a fairly large number of locations where the correlations are quite high. Again, the model is fairly unbiased, and the root mean square errors that we get are about the order of less than are usually less than 30%. Comparing it against the fire radiative power data, so the live field moisture content data from the AFMS and the predicted live field moisture content data have similar kind of distribution at different land use classifications. You could see that over grasslands there's a bit of overestimation in the predicted live field moisture content data, which is actually the bottom panel at the left, but over savannas and evergreen broadleaf forest, it's fairly it is able to estimate the live field moisture content with good accuracy. So in summary, the Australian Flammability Monitoring System, live fuel moisture content data, it provides a very good opportunity to benchmark, calibrate, or develop models for live fuel moisture content data. So it's a high resolution data sets. On comparing our Jasmine soil moisture data sets with these live fuel moisture content data, we generally found that the soil moisture is a leading indicator of the live fuel moisture content. We also found that the drought factors have a strong correlation with live fuel moisture content, especially over grasslands and croplands, but the relationship is weak over forests and woodlands. So we constructed some simple regression models based on soil moisture content to predict the live fuel moisture content, and we found that the scale varies, even though the model where we consider an annual cycle of live fuel moisture content and soil moisture content provides a better skill, and it also indicates that there are additional factors that influence the live fuel moisture content seasonality that need to be taken into account if we want to get the live fuel moisture content temperature dynamics correctly. So the way forward, like I said, I mean, this has been a small project, so we already did some preliminary analysis, but we could apply we only applied very simple regression models here, but we could apply some advanced machine learning techniques and see whether some skill can be gained in that respect. Also now there's a lot of there are recent studies which were looking into different factors which influence the live fuel moisture content and whether they could develop any physical models using all those factors, but mainly these studies has been over selected locations using observation data and things like that. So so I think it's still a relatively new field in the sense that the interest has been increasing recently, but there are still a lot of work to do in this space. The other thing I want to mention is so there are a lot of other parameters which the land surface models can estimate, like stomatal conductance, leaf area index, vegetation water stress, which could potentially be related to the live fuel moisture content. You know, something we could look into look in the future if we have the opportunity to do so. All right, I think that's from me. So I just want to thank everyone for attending, and like I said, this is probably my last talk on a topic related to this project. So I want to take this opportunity to thank my co-authors, also my project board members, especially colleagues in the Bureau, Beth, Pete Stanley, Jeff Capert, Chun Chu, the late Ian Grant, who has been very supportive, Andrew Frost, Stephen Morgan, etc. And also thanks to all the end users for your support. All right, thank you very much.
Okay, I have to unmute to clap. Thank you very much, Vinod. Especially thank you for being patient, speaker and audience, with the technological difficulties. I was very pleased we could invite guests, and apologies that we're still learning the technology in some other ways. So over to audience members, if you have any questions for Vinod or any comments for him.
Hi, Vinod. It's Hujiang here.
Yes, Hujiang.
Yeah, I have a question to you, Vinod. Is regarding to the live fuel moisture content. When you are asked, I was doing some quick Google searching, and looked to me, live field moisture content is really looking at the greenness or fresh greenness of vegetation conditions. So if you look at your correlation between the soil moisture or whatever and the live field moisture content, it's low for forest. So that is really a very complex processes controlling how the soil moisture being used by the vegetation for evapotranspiration. So I feel probably the root depth can be a very important factor to transfer how much wetness in the soil column can be transferred to the condition of vegetation above the ground. What do you think?
Absolutely. Like I said, I mean, you know, it's a very complex factors, and there are a lot of factors which can modulate the live field moisture content. Like, for example, there was a recent study done in Spain which showed that the plant physiological traits play a big role. Like they found that the leaf water potential and root water potential and stomatal conductance actually plays a bigger role than soil water availability. So, you know, this is a very high non-linear process. So it's yeah. So I think you're right. That's what I would say. So there are other factors, and also how trees or plants access water. So for example, sometimes the root depth could be much deeper than the soil profiles that we've been using here.
So if we use kind of observed NDVI or leaf area index, remote sensing based, would you say the results will be improved to look at soil moisture and the live field moisture content?
I think so. So recently we had a chat with Sujay Kumar at NASA, who were looking into something called vegetation optical depth, again, which is I think is a proxy for the plant water content, and they actually found very good correlation with the leaf area index and the vegetation optical depth. So this has been derived using the micro observations. But I think that also suggests that leaf area index or any sort of greenness indices would have some sort of relationship between live field moisture content. But like I mentioned, I mean, our focus was just on kind of finding a relationship between the Jasmine soil moisture content and the live field moisture content. So we haven't looked into any other parameters.
Right, thank you.
Vinod, have you got the chat available there on your Microsoft Teams? We've had one comment from Matthias Bauer about definition of live field moisture content, and a couple of questions from Peter Steinle that he's put up on the chat. One saying, would the live field moisture content be more responsive to a lagged and smooth time series of soil moisture, possibly allowing for days below critical threshold? And the other asking about, in the mountains, would the lateral flows of soil moisture or groundwater be an issue that... So if you'd like to comment on any of those, feel free.
So, you know, in response to Matthias' question, so like I said, I'm not an expert in live field moisture content, but I do know that it's actually the ratio of water weight in a particular sample of species. So it's basically a ratio of the weight of the water in a particular fuel sample to its dry weight. So traditionally what they have done is they weigh it before drying and then after drying and then take a ratio of it.
That agrees with what Matthias says. Yeah.
Yeah. So in response to Pete's question, like I showed, when you smooth the soil moisture data set, you could actually find an increase in correlation. And probably soil moisture would be able to predict the more of a long-term variation in live field moisture than the short-term variations, because there is always a lag in water uptake by the plants, as far as I understand. Again, I'm not an ecologist and not an expert in this field.
Yeah, I mean, that's what I was thinking, that plants taking up water would be some sort of smoothing process, and also the lag, of course.
Yes, and also it depends on the what they call the vegetation water stress. So which is a function of soil moisture, but it's not a linear function. It's a non-linear function. So there are other things.
You'd want to take out, also allow for times when the whole thing just collapses and then it just doesn't take up water, which is probably an indicator that some sort of machine, maybe it is makes you sort of think that machine learning would be throwing all these sort of variables into machine learning might be a
yeah. I think one of the key motivation to use say land surface-based model products is that you could actually you could get more sample, you could derive a live field moisture content data which has much higher sampling density, and also in a predictive as a predictive tool. You could actually use that because these are really available from, say, for example, hydraulical models or land surface models.
Yeah.
So like you could probably check in a lot of variables that can come out of land surface model, like storm-metered conductance and leaf area indices and etc., to machine learning, and see whether you could get some skill out of it.
And I was just wondering whether the results on Tombarumba, totally unrelated, whether that's just because their soil moisture, well, for trees, large trees, you're going to be bothered with lateral movement of.
I think so. That's probably why over forested areas it doesn't provide much skill, because possibly the roots are much deeper and the trees are accessing water from much deeper soil profiles than what LSM predicts. So there are a lot of processes that's not parameterized, for example, with groundwater in Jasmine. So yeah.
Sounds like we need hydrojoules or something like that. That's all that, isn't it?
Possibly.
Okay, done.
And the case hydrojoules. Yes.
Okay, last chance if anyone else wishes to, then unmute and jump in.
Can
But
you
go,
hear me?
thank you. Yes.
Yeah, just Pep Canada. Look, I just want to make sure that, so if you look at the ecological literature of fire risk in forests in Australia, the most determining of fire risk is the fuel loads of what they call fine and coarse, particularly fine litter. These are now dead mass, and the moisture content of it. So I guess, and the most common fire is also understory fires, which they really kind of are driven as they say, by these fuel loads and content, moisture content. So I just want to make sure that as you move and you progress with these relationships and how you want to apply them, that we're careful also how this thing gets applied, because the live fuel moisture, it is not one of the important determinants necessarily of this fire risk. And when canopies and big trees, they really get into the fire, it's when we have these much bigger, super hotter fire areas, which the whole fire behavior and risk really is determined by the actual weather itself more than the condition of the forest. So, yeah, it's just, I guess, I know that it has taken a bit of discussion here to understand what the live fuel is, and I also search myself as you were talking. And yes, that's indeed the live components, which probably are relevant for maybe open woodlands and rangelands where the grasses dominate, the biomass. But I think that for forests, the fact that you don't see that stronger relationship, it's not surprising, because I think that it has been established that what's most important is not the live component, is the dead component. So this is not a criticism, it's just to say, as you move forward to kind of do applications, and just be careful how this thing gets applied, at least to the forests of the south and southeast of Australia, because they certainly behave quite differently in terms of what's really a fire risk factor. Of course, when everything is so dry and you dry everything, so basically, all the fuel, dry fuel and dead fuels, plus some of the plants, then of course everything could be related. But most of the fires are actually understory fires, and they're driven by that dead component.
Okay, yeah, thanks, Pep. That's a good point. Yeah, I mean, we haven't done any comparison with the dead fuel moisture content, and yeah, I'm not even sure whether that kind of data is available, but that's something that would be interesting to look into.
Vinod, my understanding of MacArthur's work was that it was on leaf litter, so on dead fuel. That was
Yeah,
the drought factor. I mean, I'm not sure about literature since then about where the strongest correlations is, so I'll just have to take Canadel's comments on that. But yeah, I think the drought factor was designed for leaf litter, so dead fuel.
Yeah, the drought indices used in the drought factor is basically, the Keys-Byron drought index or the soil dryness index. We found that it actually generally resembles a soil profile of about 1 meter deep.
Yes, sorry, that's the drought index part of it, but the drought factor, which uses a short term.
Yeah, I think so. Yeah. So
anyway, thank you, and thanks, Canadel, for the comment. Okay, any last ones before we close this? That's not just I will stop the recording. I will formally thank Vinod, but it doesn't stop people staying online to talk to him a bit more.
Matthias Ball wanted to respond to Pep's.
Matthias? Yep,
yes, thanks for that. I was just typing in the chat in the chat channel, but no, I just wanted to respond to what Pep was saying, that it's definitely both live and dead fuel moisture that matters. So in some work we did a few years ago for Southeastern Australia, that was Nolan et al., Rachel Nolan's work. In geophysical research letters, we showed that there's threshold behavior in the accumulation of burned area in response to dead and live fuel moisture. So for both, you can show that forest fire activity, and also in other vegetation communities dominated by woody vegetation, definitely responds to both dead and live fuel moisture. The dead fuel moisture in general is a little bit more responsive to daily variation in atmospheric moisture content, for instance.
Yeah.
Whereas, of course, live fuel moisture is buffered by the soil. So the fact that you found relatively low correlation between predicted soil moisture and live fuel moisture in forests, I think, is definitely due to the rooting depth issues, and basically you're missing the whole physiology between soil moisture and leaf response, so that's why the correlation is not that high yet. Need to solve for the ecophysiology that happens in between.
Yeah. Thanks, Matt. Yeah, I think I agree. Yeah, you have to consider the plant physiology as well in order to get the live fuel moisture content correct, not just the soil moisture. Yeah.
Okay, thank you very much. And I see Pep Canadel's also acknowledged that in the comments. I might bring this to close just on the time, but as I said, if you want to hang on and ask Vinod questions, that doesn't stop you. But just formally thank Vinod very much again for the talk, which has certainly prompted some interesting discussion, some interest, and for persisting with the technology. So thanks, Vinod.